Hey there, today we're jumping into a really classic networking puzzle. How do you make TCP, which is pretty much the engine of the internet, actually work well on mobile networks that are, notoriously unreliable? We're going to look at three foundational ways people tried to solve this. All right, let's get into this three-way showdown.
So here's how we're going to break it down. First, we'll talk about why TCP even has a problem with mobile in the first place. Then we'll meet our three contenders: indirect TCP, snooping TCP, and mobile TCP. And to wrap it all up, we'll put them side by side to see how they really stack up. Let's do it.
So what is the big deal with TCP on your phone? I mean, it works, right? Well, yeah, but it all comes down to this one single, really flawed assumption that's baked right into the DNA of TCP. You have to remember, when TCP was first dreamed up, the internet was all physical cables. And in that world, if a packet of data just vanished, it was almost always because some router down the line was totally overwhelmed. Network congestion. So TCP's built-in reaction was simple. Whoa, everyone, slow down. Let's ease the pressure.
And this is where it all falls apart for mobile. On a wireless network, packets get lost all the time, for reasons that have nothing to do with a traffic jam. It could be radio interference, or you're just moving between cell towers. But old-school TCP, it has no idea. It sees a lost packet, it assumes a network is clogged, and it just slams on the brakes. The result? Your connection slows to a crawl. And that is the exact problem these three solutions we're about to see are trying to fix.
First up to the plate, we have indirect TCP, or I-TCP. The easiest way to think about this one is as a divide-and-conquer strategy. It basically decides that the wired and wireless parts of the internet are so different, they shouldn't even be in the same connection.
So the core idea here is to literally break one long connection into two completely separate ones. You've got your standard, happy TCP connection running over the stable, wired part of the internet. Then, right at the edge, a middleman takes over and starts a totally new, separate connection to your phone, one that's built specifically for the chaos of a wireless link.
And you can see that middleman, the foreign agent, right here in action. The sender, or the correspondent node, fires off a packet. The foreign agent gets it and immediately sends back an I got it message, an ACK. So the sender's happy, it thinks the job is done. But really, the foreign agent now has to handle a whole second separate journey for that packet over the shaky wireless link. It's kind of like a relay race where you pass the baton to another runner who's about to run on a totally different, much tougher track.
Now, the huge advantage of doing it this way is isolation. Any craziness happening on the wireless side, lost packets, errors, you name it, gets handled right there by the foreign agent. It never bothers the original sender. So the wired part of the internet just keeps humming along smoothly. Plus, you don't need to change anything on the server side, and you can fix errors super fast on that short wireless hop.
But, and this is a massive but, there's a huge trade-off. This whole approach breaks one of the golden rules of the internet, the end-to-end principle. When the sender gets that confirmation message, it no longer means your phone actually got the data. It just means the middleman did. That foreign agent also becomes a single point of failure, not to mention a potential security nightmare.
Okay, so if completely splitting the connection is, a little problematic, what about something a bit less drastic? Let's bring in our second contender, snooping TCP. This one takes a totally different approach, more like eavesdropping.
Snooping TCP is a lot more subtle. The foreign agent is still there, sitting between the wired and wireless worlds. But instead of splitting the connection, it just watches. It snoops on the packets flying by, keeping a copy of the data just in case something goes wrong on that last wireless hop.
And you can see how it works right here. The end-to-end connection stays completely intact, from the original server all the way to the phone. The foreign agent just buffers the data and listens for the acknowledgments coming back. If it notices a packet got lost, it jumps in and resends the data from its local cache, often so quickly that the original sender, who might be halfway across the world, never even knows there was a problem.
So the huge win here is that you preserve that true end-to-end principle. When an ACK gets sent, it really means the mobile device got the data, period. Just like I-TCP, you don't have to change anything on the fixed hosts, and since the connection isn't formally split, moving between cell towers and new agents is way less of a headache.
But of course, there are downsides. The isolation is nowhere near as good as with I-TCP. If the wireless link gets really bad, the original sender might still time out and slam on the brakes anyway. And here is the real kicker for the modern internet. If the traffic is encrypted, the foreign agent can't snoop on the important bits, and the whole clever scheme just doesn't work.
All right, our third and final approach, mobile TCP, or MTCP, comes at this from a slightly different angle. It's less worried about those tiny momentary packet losses and way more focused on handling longer, more frequent disconnections. Think about when your phone loses signal going through a tunnel.
MTCP actually brings back that split connection idea from ICP, but it has a really cool trick up its sleeve. Its whole purpose in life is to manage total disconnections gracefully. It uses what's called a supervisory host to watch the connection. If your phone suddenly goes offline, this host does something brilliant. It tells the original sender to shrink its sending window all the way down to 0. By setting that window to 0, the supervisory host basically tells the original sender, hey, just chill out for a second. Stop trying to send data and just wait. Don't panic and drop the connection. It's like hitting a pause button on the entire transfer. Once your phone gets a signal again, the supervisory host tells the sender it's okay to open the window back up, and everything picks up right where it left off. So the obvious advantage here is that it's fantastic at handling those complete disconnections, which neither of the other two were really designed for. It also manages to keep the end-to-end semantics intact, and it avoids some of the messy problems you can get when you're moving between networks. And the downside? Well, a lot like Snooping TCP, it doesn't do a great job of protecting the wired network from wireless errors. Any packet loss that isn't from a total disconnection can still make its way back to the sender and cause a slowdown. It also means you need some special software on the mobile device, and it adds a little bit of processing overhead.
Okay, we've met all three contenders. Now it's time for the final showdown. Let's put them all on the board and see how they stack up, head to head.
This table really tells the whole story. You've got indirect TCP, which goes for that clean break. Its biggest win is that amazing isolation from wireless errors, but it comes at the huge cost of breaking end-to-end semantics. Then there's Snooping TCP, the quiet observer. It's awesome because it keeps those semantics pure, but it offers pretty bad isolation and hits a wall with encryption. And finally, mobile TCP. It also splits the connection, but it's laser-focused on handling disconnections. It keeps the semantics, which is great, but just like Snooping TCP, it doesn't really protect the main network from wireless hiccups.
When you boil it all down, all three of these classic approaches are wrestling with the exact same fundamental problem. It's a trade-off. Do you prioritize completely isolating the messy wireless link, the way I-TCP does, or is it more important to preserve the pure end-to-end design of TCP, which is what Snooping TCP and MTCP try to do? It really seems like you can't have it both ways.
And that really brings us to the final question to think about. I mean, these were early, foundational ideas, but that core conflict they uncovered is still incredibly relevant today. In our world of 5G, constant video streaming, and the Internet of Things, which philosophy actually makes more sense? Is that perfect isolation worth giving up a core principle of how the Internet was designed to work? Or is it better to stick to that principle, even if it means dealing with some performance headaches? Something to chew on. Thanks for tuning in.